Today we will cover part 2 of supporting OpenJDK's method handles in OpenJ9. I am Babneet Singh from the VM team, and I also have Nazim from the JIT team who will be presenting along with me. A brief overview of part 1. In part 1 we covered why the invoke package was needed, and then we looked at the public API that allowed us to create method handles. And then we looked at the method handle and its internal elements. And then the presentation ended with the 4 lifecycle stages of a method handle, where we deconstructed a method handle example while illustrating the 4 lifecycle stages. Here we can see the method handle and its internal elements. Method handle has a Lambda form which generates custom bytecodes for it. And a Lambda form has an instance of member name, which points to the method that encloses the bytecodes generated for a Lambda form. So this is how a method handle looks, and the 2 key internal elements of a method handle are Lambda form and member name. In part 1, we saw the 4 lifecycle stages. The first one was compilation via Java-C, where we just compiled the method handle example via Java-C, and we showed what bytecodes are generated. In stage 2, we showed where in those bytecodes the method handles get created and how the internal elements of the method handle are initialized, the Lambda form and the member name. In stage 3, we looked at linkage, which creates the dependencies that are needed to invoke or execute the method handle. And in stage 4, we showed how those dependencies were used to execute or run the method handle. In part 2, we will cover more examples where method handles will be used. Then we will sum up all the VM support that was seen in those examples. In addition, we will cover some support which was not covered. Then we will look at diagnostic features, which can be used to triage failures or understand perf issues related to method handles. Then there will be a transition to Nazim, where he's going to discuss about JIT support, what changes and what dependencies we needed over there in order to support OpenJDK method handles. And then there's going to be a failure example of a failure and how it was triaged, which is going to be JIT focused. So we will begin with VarHandles, which is another use case of method handles. So why VarHandles are needed? Because it is a safer alternative for the Unsafe API. It is type and memory safe, which the Unsafe API is not, but it has similar performance as the Unsafe API. And since its introduction in Java 9, it is widely used in the JDK. Few key projects with it, where it is extensively used, is the value types project and the project Panama. So before we dive into VarHandles, let's see why Unsafe is bad. In this example, there is a class test, and in this class there is a field, an integer field named test_var defined, and we are using the Unsafe API in this example to modify the test_var field in class test. Unsafe lets us find the field offset for this test_var, and then we use the Unsafe's put_long method to update the field. The issue over here is that the field is an integer, but we are doing a put_long, which puts a long value in an integer field, and this violates type safety So this is one of the examples where Unsafe is bad and it compromises the safety of the JVM. And when we look at VarHandle, we will see how these safety issues are addressed and how VarHandles makes it safer in the JVM. So what's the difference between a method handle and a VarHandle? A method handle is a typed, directly executable reference to an underlying method, constructor, or field, whereas a VarHandle is also a typed reference, but it only focuses on fields, array elements, and off-heap data structures, which corresponds to memory addresses. A method handle is directly executable, whereas a VarHandle can only be executed through one of its access modes. Access modes refer to the operations which can be used to manipulate the entity that the VarHandle represents. What are the different access modes that VarHandle supports? There are 5 different types. There is read, write, and 3 variants of atomic updates. Each access mode has a set of operations. For instance, read. With read, you can do get volatile, get acquire, etc. And in total, there are 31 access modes or 31 different operations that can be performed on a VarHandle. These are the operations which are equivalent to what one would see in the Unsafe API. And these operations are very specific to what can be done on a field or a memory address. So here is a VarHandle example. The same test class that we saw in the Unsafe example is seen here. The only difference is that we are updating the field test_var via the VarHandle API instead of the Unsafe API. The key elements in this example is the creation phase where the VarHandle gets created. For the creation, we are calling the find VarHandle method in the lookup class, which takes 3 input parameters. The first one is the name of the class where the field exists. Then we're providing the name of the field, and we're also giving the type of the field. And this is where the VarHandle API is going to enforce the type safety, which was not enforced in the Unsafe example. So providing type allows the VarHandle API to enforce type safety. Further down, we are seeing execution of 2 access modes. setVolatile will set the field to the specified value, and getVolatile would retrieve the value of the field, and then we are doing an assertion to make sure that the value is correctly set. So this is a simple VarHandle example, and we are going to deconstruct it and see how the JVM handles this example, similar to what we saw for a method handle in part 1. So the first phase in this VarHandle example is creation of a VarHandle instance. There are methods in the lookup class which allows us to create a VarHandle. In the previous example, find VarHandle was used. There are other methods such as unreflect VarHandle, and there are a few more which will allow us to create a VarHandle. The return value from these methods is going to be an instance of VarHandle, and there is an object layout for the VarHandle shown in the slide. The key things to note here is that the object contains an array of member names and an array of method types, and the array is sized to the number of access modes that this VarHandle supports. So for instance, access mode getVolatile will have its own member name and method type. And the same applies to any other access mode that this VarHandle is going to support. In comparison to a method handle, a VarHandle has many member names, whereas a method handle only has one member name. So when we talk about member names, the thing that comes to our mind should be Lambda forms. Lambda forms is the invocation semantics of what the member name should do or what the member name is going to execute. And in this case, we are doing we are setting a field in a class that's the behavior that this that this Lambda form is defining. And a brief overview of a Lambda form is going to be, it's going to have a name, it's going to have an arity, which is going to define the number of input arguments that this Lambda form is going to take. And then there's going to be a number of temporary expressions, which will have a type associated to it and the function that it's going to call, along with the arguments that are going to be passed to that function. And at the end, this Lambda form is going to return a result, which in this case is void. So it's going to return nothing. So this should be a brief overview of what a Lambda form is from part one. And this Lambda form is going to be used for the set volatile access mode that was shown in the VarHandle example. From a Lambda form, we get bytecodes, and these bytecodes correspond to the Lambda form which was shown in the previous slide. The 3 input arguments are annotated at the top, and the 4 temporary expressions T3, T4, T5, and T6 are associated on the side. The function calls get translated into bytecode instructions, and the values returned from those function calls are being passed via other bytecodes such as A loads and A stores. And at the end, we are doing an invoke virtual with unsafe put int volatile, which should update the field in the class. So the last 2 stages of the VarHandle example are linkage and invocation. These 2 stages correspond to the invoke virtual bytecode being executed on the VarHandle's access mode function, which in this case is set volatile. So how does the interpreter run this invoke virtual bytecode on the VarHandle access mode function? It's going to convert it into an internal bytecode named invokehandle, which is completely identical to the MethodHandle example where we converted the MethodHandle.invoke and invoke exact calls to the same bytecode. The first step is linkage, where we're going to generate the dependencies that are needed to execute the VarHandle's access mode. And this happens via an upcall to a Java method. So we are calling a Java method from native code, and this method is named MethodHandle natives.link method. It's going to give us 2 values. One is a member name, and the other is the appendix. The member name is going to point to a helper method, whereas the appendix is going to return an object that needs to be appended onto the stack in order to execute this helper method. So once linkage completes, what we do is we append the appendix on the stack only if it's not null, and then we're going to execute the helper method. And in the context of the VarHandle example shown earlier, this helper method is going to do some due diligence, which is going to make sure the right arguments are on the stack, and then it's going to call the setVolatile member name, the member name for the access mode, which is going to be the setVolatileField cast lambda form that was shown earlier. So to compare this with the MethodHandle example, which was shown in part 1, the left side has the invoke virtual on a MethodHandle invoke, and the right side has an invoke virtual on the VarHandle access mode operation. The key differences are highlighted in red. In case of method handle invoke, the two arguments are different. The first argument is a method handle and the last argument is a method type. Whereas in the VarHandle example, the first argument is a VarHandle and the last argument is an access descriptor. In the method handle example, we already know what the method handle is, so we are just doing some due diligence, which is to make sure the type is of the correct type, and then we are making sure if we need to customize the method handle, and then we are invoking the member name which the method handle points to, and that is the setVolatileField class method, for which the Lambda form was shown a few slides earlier. Whereas in the VarHandle example, we don't know what the method handle is, so we have to retrieve the method handle from the VarHandle. And to find the method handle for the access mode, we are giving the access descriptor into the API, and it retrieves us the method handle for that access mode, and then we are doing a type conversion. As type will convert the method handle so that it matches the access mode's method type. And method type is just a description of what the return type and the input parameters are for the VarHandle's access mode. And then at the end, we are doing the same operation that we did for the method handle invoke. We are going to call invokeBasic on the method handle's member name, which is going to be the setVolatileField cost method. So this slide should highlight the differences between how MethodHandle.invoke and VarHandle.access mode operations vary. There are other use cases of a method handle. So method handles can be used for the invoke dynamic bytecode, and then they can also be used in the LDC bytecodes for certain constant pool entry types. So let's begin with invoke dynamic. So invoke dynamic was introduced in Java 7 to support dynamically typed languages. In Java 8, it was further used to support Lambda expressions, and in Java 9, it was used to support string.concat. So we will look into more detail at the string.concat use case of invoke dynamic. Prior to Java 9, this is how string.concat was handled. So in this example, we are concatenating two strings, cute and dog, and the corresponding bytecodes for this example in Java 8 will look something like this. It's going to heavily rely on string builder, and one would say string builder is very efficient and well designed, so why use invoke dynamic for string concat? And the reasons for this are that because invoke dynamic provides a more dynamic approach to adopt a more optimized concat strategy. So without changing the bytecode. So if we were to use something other than string builder, we will have to recompile the code, and invoke dynamic will allow us to use a more optimized strategy for string concat without recompilation. And the other advantage of using invoke dynamic is that it is smaller, less bytecodes are needed, so it takes less footprint. So how invoke dynamic gets used for string concat is shown on this slide. The same example in Java 9 will look as follows. All these string builder bytecodes are replaced with a single invoke dynamic bytecode, which means less memory will be used to store the bytecodes. The invoke dynamic is associated to a bootstrap method. The bootstrap method defines what kind of helper method needs to be created in order to do this string concat example. And while creating this helper method, it's also going to create method handle, which is related to the constant method handle constant pool entry. So let's first look at how the invoke dynamic bytecode gets handled by the JVM. It has a very similar process to what we saw in the previous VarHandle example. There's going to be linkage, and the linkage is going to be performed via an upcall to MethodHandle-link call site. It's going to return the exact same entities that we saw in the previous example, a member name and an appendix. And we're going to append the appendix onto the stack if it is not null, and then we're going to run the helper method via the member name.vm target. And the second component of the invoke dynamic example is the LDC, or the constant method handle constant pool entry, which is technically the bootstrap method at the end has a reference to a constant method handle CP entry. And this entry is what defines the method handle. And if we call an LDC on this constant pool CP entry, what we should get is an instance of a method handle. So later on, I think they wanted to employ the invoke dynamic strategy also onto constants. So JVM, or the Java language, introduced the constant dynamic constant pool entry. In invoke dynamic, we delay the linking of methods for the operation. In constant dynamic, what we're going to do is we are going to delay the creation of a constant value. And how this helps is that if a constant never gets used, we're never going to evaluate the value, and we don't even need to save the value, so we will also save on footprint. And the other benefit is, since we don't need to create the value at startup, we will have a faster startup. The example over here is has a class test, and in this class we have a final integer field, which is being set via a method called getIntegerField. The constant dynamic is defined via the bootstrap method at the bottom. And if we call an LDC on this constant dynamic constant pool entry, it's going to evaluate the value of the field, the final field shown in the example. So let's quickly look at the differences between the constant method handle and constant dynamic CP entries. The differences are highlighted in red. The first difference is in the type defined. For a constant method handle, the type is defined via method type, because method handles can also execute methods, constructors in addition to fields. So we also need to know what the return and the input arguments are. Whereas for constant dynamic, the type defined can just be described via a class. And the other difference is in the return values of the bootstrap method. For constant method handle, it's a call site. A call site is just a wrapper for a method handle. Whereas for a constant dynamic, it's an object, and is sufficient to describe a constant value. So these are the two differences between constant method handle and the constant dynamic constant pool entries. Over here, we see how the LDC is handled for the two constant pool entries. Same process as previous examples, we are doing some linkage, and the linkage creates, ends up calling a Java method, and the Java method is going to return a constant value for in case of the constant dynamic constant pool entry, and it's going to return a call site or method handle for the constant method handle constant pool entry. It only happens once and we cache the value. So if we are repeatedly calling LDC on this CP entry, we're just going to restore, or we're just going to return the cached value. So at this point, I think we've seen all use cases of a method handle. Now I'm just going to sum up all the VM support that we have seen in this use cases. So these are a number of upcalls in the examples. Method handle natives.link call site was used for invokedynamic to create the two dependencies, the member name and the appendix. Method handle natives.link method was used in case of method handle invoke, method handle invoke exact, and the VarHandle access mode operations. Again, it created the two dependencies, which are the member name and the appendix. In case of the two LDCs, for constant method handle, constant pool entry, the upcall was done to method handle natives link method handle constant, and for constant dynamic constant pool entry, the upcall is done to the method handle natives link dynamic constant. So this sums up the upcalls from a VM support perspective. The other key VM support elements are the native methods in the method handle class. Invoke and invoke exact were covered in part 1, and they were also briefly covered during the comparison phase of the VarHandle example. Then there is invoke basic, which was covered in part 1, but we will review it briefly. The four elements, the four LinkTo methods shown at the bottom are something that we have not seen before. They are new. And after invoke basic, we will look into what these LinkTo methods do. So invoke basic is an unsafe, unchecked, and weakly typed version of invoke exact. It is described as an INL in the bytecode interpreter.hpp file. What it does is it reads the method handle from the stack, then it extracts one of its internal elements, lambda form, and then from the lambda form, the member name is extracted, and member name contains a pointer to the method which needs to be executed, which is VM target. So we just run the VM target method. To sum it up, invoke basic just executes the member name associated to the method handle. Now moving to the LinkTo methods. The key objective of LinkTo is also to invoke a member name. An invoke basic was an invoke virtual, whereas the LinkTo methods, all four of them are invoke static methods in method handle. For these, the member name is already on the stack, so we don't need to derive it from a method handle as we saw in the case of an invoke basic. Arguments are also on the stack, so we don't have to do any stack manipulation. The only difference is the run phase. Over here, we're going to dispatch the method that corresponds to the member name, or that's stored in the member name. By dispatch, what I mean is for LinkTo virtual and LinkTo interface, we won't know what the concrete implementation of the method is. So we have to do a vtable or an itable search to determine the concrete implementation. And that is what dispatch refers to over here. And dispatch, after finding what method to execute, will run that method. And at the end, these LinkTo methods, again, just invoke the member name. So this sums up the key features which were needed to be implemented in the VM to support OpenJDK method handles. Now let's look at diagnostic features which can be used to triage failures or better understand the behavior of OpenJDK method handles. So on this slide, I've shown 5 Java property flags. Now these Java properties enable logging or verbose output for method handles. So the first one will enable more verbose naming. The second one will write bytecodes generated for Lambda forms to a directory. The third Java property will enable verbose output for linkage paths specific to the invoke dynamic instruction. The third Java property will enable more logging for the Lambda form resolution paths, like how the member name is created and how the bytecodes are being generated. And the last Java property corresponds to Lambda form compilation failures. Lambda form compilation refers to the generation of bytecodes for a Lambda form. If we are unable to generate those bytecodes for some reason, in order to find that reason, we can enable the last Java property, and we will be able to figure out why we were unable to generate bytecodes for a Lambda form. All these Java properties are set to false by default. So if we are triaging or if we're diagnosing an issue, we have to turn these properties to true, and then we will get more verbose output or logging to figure out what the issue is. On this slide, I show 3 more Java properties. These are more Perf specific. So the first property is a threshold for compilation, Lambda form compilation. Lambda form compilation, as I said earlier, defines when to generate bytecodes for a Lambda form. And this threshold gives us the ability to control the generation of bytecodes. By default, this value is set to 0, which means we immediately generate bytecodes for a Lambda form. The second Java property corresponds to another threshold, which is related to the method handle customization. Method handle customization refers to creating a customized Lambda form for a method handle, which means there's a one-to-one relationship between a method handle and a Lambda form. Previously, the other case is where we are sharing a Lambda form with multiple method handles. So this Java property will allow us to customize a Lambda form based upon how many times the method handle gets invoked. And so we can control it via varying the threshold. At this point, the threshold is set to 127. So which means after 127 invocations of this method handle, we will customize it and create a custom Lambda form for it. The last property refers to inlining a method handle in JIT. It's again a threshold, and threshold applies to how many on the invocation count of a method handle. It only applies to a certain kinds of method handles. Currently, OpenJ9 does not obey do not inline threshold because this work is still in progress. It may have been merged, but last I was told it's still work in progress, and the PR I think has been opened by Devin Pepino. But once that PR gets merged, we will be able to provide a threshold for this do not inline Java property, and then we'll be able to control when to inline a method handle in JIT compilation. So from a diagnostic perspective, the last number of things we need to be aware of are the annotations. Now these annotations are again divided into 2 different kinds, debug and perf. Under debug, there's compiled. The compiled Java annotation is attached to any method which contains bytecodes generated by Lambda form. And the hidden annotation is also attached to frames which are supposed to be hidden in stack traces, and the methods that are generated for Lambda forms also have this hidden annotation associated to it. So any code, bytecode generated for a Lambda form are hidden by default. So we need to, if we are triaging an issue, we would need to see what the stack traces for the Lambda form generated bytecodes look like, and for this, we have to enable them by this command line, the shown hidden frame command line option. And the other perf annotations provide hints to the JIT to do a specific optimization. For instance, the stable annotation tells the JIT to do constant folding for final fields and array elements. The force inline annotation tells the JIT to inline a specific thing, a specific entity in the JIT, and the don't inline annotation tells us never to inline that entity in the JIT. So these annotations are used in the OpenJDK implementation, and we need to be aware of them in order to better debug or understand the perf, or better debug functional issues, or better debug perf issues. So I think with this, I will transition to Nazim, who is going to discuss more about JIT support.
Thanks, Billy. So to recap, the benefits of moving to the OpenJDK implementation, basically every single method handle related method is going to be treated like just like any other Java method, instead of each and every method handle component having to have some sort of custom handling and handcrafting a lot of the IL involved. And that is a very complicated process and prone to errors, and any new features that we want to support requires a lot of work on both the JIT and the VM side. But OpenJDK implementation simplifies a lot of that. And in this part of the talk, I'm going to focus on highlighting some of the key implementation that had to be done in the JIT to support OpenJDK implementation. So firstly, we had to have a new handling mechanism for invokedynamic and invokehandle bytecodes. So we already had support for that, but for OpenJDK implementation, we had to do that differently. Each of these bytecodes have corresponding invoke cache entries containing information about the call. And depending on which bytecode they are located in different places. So for invokedynamic, we obtain it from the call site table. And for invokehandle, we obtain it from the method type table. And the call site index and the method type index, those are encoded in the bytecode. So we use that to look up the right invoke cache entry. So an invoke cache entry is a 2-element array containing Java object references for the member name and the appendix object. So now when we have a resolve invokedynamic and invokehandle, what it means is that the corresponding invoke cache entry is resolved. If it's not, then it's not a resolve call. So for resolved invokedynamic and invokehandle, we construct the call to the target method during ILGen, and that target method is obtained from the member name object in the in the invoke cache entry. And finally, if the target method expects it, we push the appendix object as the final argument. And here's an example of how a call can look like that is resolved. However, when that invoke cache entry is not resolved, we still construct a fake resolve method to MethodHandle.linkTo static. So this is a VM internal native library function, and dispatching into it means transitioning to the VM to handle that. So the link to the static helper at runtime sets up the call to the target method. However, the JIT code has to provide a few things in order to do that. So from the JIT code, before we dispatch into the link to static helper, we need to have the on the stack the explicit arguments for the call, and then the appendix object address, the member name object address, and the number of slots occupied by the arguments, so that we can locate the beginning of this of the stack specific for that call. And we also need to indicate that we may have pushed a null appendix object address because we are not able to check it at compile time. So we just provide the address and we just notify the link to static helper to kind of check it at runtime to see if it's null or not. So here's how a call to link to static is going to look like. In this case, we took an invokedynamic bytecode, and we saw that the call site table entry was unresolved. So we have loads of the two elements from the call site table entry, and have a link to static call with the appendix and member name objects added as the last two arguments. We just showed one of the INL calls we use for unresolved invoke dynamic invoke handle. So there are various other INL calls, namely INvokeBasic, and the other LinkTo methods, such as LinkTo virtual or LinkTo special. So these are all VM internal native functions, and they are signature polymorphic, which is why we need to communicate to the VM how many arguments are there in the call, so that it can locate the beginning of arguments. So for that piece of information, we pass it on through by setting the VM thread.temp slot field to the number of stack slots occupied by the arguments. And then the other issue that we spoke about regarding unresolved invoke dynamic or invoke handle is that we may have pushed an appendix object that may not be needed in the actual target method. And we need to communicate that this is a fake resolve method, and possibly something that needs checking whether there's a null appendix object or not. So we set VM thread.floattemp1 to a non-negative value to indicate that there may be a null appendix in there. So otherwise, the default value is -1. So there are a few considerations for OSR as we push the appendix and member name object to the invoke dynamic and invoke handle call. We may have to make sure that we don't push these implicit arguments because they're not part of the method signature. So the bytecode behavior results in these objects being pushed anyway. So then we would have duplicates in the stack, which is why when we set up the list of arguments that we want to stash for OSR, we need to skip over these arguments. As part of the optimization work, the MethodHandle Transformer is one of those optimizations we've introduced as part of the OpenJDK MethodHandle support. So for a lot of the transformations, it requires knowledge of object info of certain nodes around the possible sites of transformation. There are mechanisms in place to obtain the object info of autos through reverse post-order traversal, because we do not always have that information available. and one of the main things that MethodHandle Transformer does is to transform INL calls into target methods when we have the known object information needed to determine the target methods. And in many cases, we transform or eliminate trees that can be simplified into more better performing operations and squeeze out as much performance as we can. And for example, let's discuss MethodHandle.linkTo virtual transformation. So in order to transform that into something into the dispatch into the virtual method instead of going there through the INL call, we first try to take the member name and see if we have known object information. So the member name for link to virtual would be the last argument of the call. And from there, we can then obtain the target method from the member name, and we can start to call for that. And then we obtain the JIT vtable index from the member name. Well, originally it stays as interpreter's version of the vtable index, and then we convert that into something that is appropriate for the JIT. And then we construct a virtual call into the vtable entry. And the vtable entry is either going to have a thunk for an interpreted method or the JIT method address if it is compiled. And that results in a much faster dispatch than doing it via link to virtual. So at compile time, we may not always have the necessary object information of nodes around INL calls. And that can be a problem because INL calls have a significant impact on performance as they require J to I transition. And if the final target method is that we dispatch to via the INL call is compiled, then effectively what we do is a J to I transition and then an I to J transition to get to the JIT method, and that is not an ideal state to be in. So to prevent this, we have a transformation implemented in recognized call transformer, where we construct trees to check if a target method has been compiled at runtime. And if it is compiled, then we are able to bypass dispatching into the INL call and instead go directly into the JIT method address. And here's the diagram of how this looks like. So we take a method handle linked to something, and then in order to determine whether it is compiled, there is a bit in J9 method.extra field that we mask out to where it is 0 if it is compiled. Otherwise, we dispatch through the original call, and then so as soon as the target method gets compiled, the execution gets much faster. So to explain the general idea of how we create these trees, so if, as I mentioned before, if the method is compiled, then the J9 method.extra field, the last bit of it is going to be 0. And then from the value of the extra field, we can calculate the compiled method address at runtime. And then we represent the indirect call into the JIT method address using 2 different helper methods we introduced in JIT helpers. One is dispatch computer static call. We use it for everything other than link to virtual, and for link to virtual, we use JIT helpers.dispatch virtual. And if target method is not compiled, we just default to the default to dispatching via the INL call. So for all of these, we need, So for all of these, we need to access the J9 method corresponding to an INL call at runtime. So we need to construct trees to perform a chain of loads in order to get to the J9 method. So for handling invokeBasic call, we start from the MethodHandle object, which is the first argument of an invokeBasic call. And from that, we can obtain MethodHandle.form, which is the Lambda form object. And from Lambda form, we can get the VM entry. So it's Lambda form.VM entry is the member name. And from member name, we can get the J9 method, which is the VM target field. For a MethodHandle.linkTo methods, we already have the member name as a last argument of the call, so we just start from there. So now coming to the challenges of debugging MethodHandle-related issues, I think this was important for us to highlight that because there is an increasing use of MethodHandles throughout the JCL. So chances are we will come across issues that either are perhaps implementation related or some other problem that highlighted as a result of the MethodHandle related as a result of changing to the OpenJDK implementation. So, and one of the issues is that the MethodHandle related crashes have often been difficult to reproduce. And a lot of the failures involve Java runtime exceptions, and they don't, and which is why they don't generate core files for us to look at right away unless we configure a dump agent. And the other challenging bit is that the error outputs are not sufficient in classifying the crashes themselves. And finally, it is also hard to narrow down to the methods that, the smallest set of methods we need to compile in order to reproduce it, mainly because the Lambda form generated methods have different names in each session. So it is hard to really binary search our way through limit files in order to narrow it down. So here's an example of how it can look like. A MethodHandle-related failure can look like. You may see various Lambda form generated methods with 0x00 and something .invoke or .invoke underscore method type. And they can exist in multiple places in the call stack. And I guess if it is very close to the site of exception, then the chances are high that it is a MethodHandle related problem. So like I mentioned earlier, it is hard to binary search your way through the limit file, mainly because of the number of the runtime generated Lambda form methods that we have to go through. And this makes it difficult to really use a binary searching method to narrow down to the failing methods. So here, if we just remove the other methods that are not part of that, so as you can see, well, I hope it helps you see it more clearly, but we have many methods that, for example, invoke here has the exact same signature, but then they're entirely different methods, part of different class names. And if I was to run this again, for those exact same methods will have different class names. So there really is no easy way to kind of omit that, which is why we need to be a little more creative in how we try to narrow down to the issues. I can spend all day talking about different the ways we can debug this, and it's really hard to explain through a single example, which is why I'll just highlight some of the top three ways that I found was most helpful in diagnosing MethodHandle related issues. And because we have a problem with reproducing the problem and trying to get a core file, and often they're in tests where it takes a while to run them. So I found it very useful to kind of modify the test scripts and just enable a limited set of test cases leading up to the failure to see if we can reproduce it, and that can significantly improve the chances that you'll be able to get the diagnostic files you're looking for. After you obtain the core files, I found it helpful to use JDMView and KCA to examine frames leading up to the crash. And this helped me identify some the methods that are very essential to reproducing a failure. And in addition to using limit file binary search, we also need to exclude the lambda form generated methods from them in order to narrow down to the smallest set of methods we need. So in this case, an XJIT exclude option is very useful, where we can have regular expressions with wildcards that represent the lambda form methods we're trying to eliminate. And you'll have a lot more success with that than just using limit file binary search. With that, this concludes our talk, and here are some of the references we've used in order to prepare this talk. And there are also excellent resources for you to learn more about method handles and how to work with them. And if you have any questions, we'll be happy to answer them. Thank you.
Any questions? Okay, if not, Abneet and Nazim, thank you for taking us through 2 presentations worth of content on this fairly complex topic and distilling it down into something that is is going to be useful for others to learn more about this. So, last call for questions. If not, we'll end here.
Great talk, guys. Thank you.
Okay, thanks everyone.